one of the problems about getting older. Tend to forget a couple of things. So let me make sure this YouTube is up and running. Okay, so, all right. So YouTube is up and running. So let me go back to the PowerPoint here. Can you all see my screen? Yeah, okay. Okay, good, thanks. So as I was saying, what is being shown here is, if I'm not mistaken, lead 2 iodide, being added to a solution of either sodium or potassium nitrate, doesn't make a difference. And what will happen is that you're going to end up with a precipitate. Actually, this should be lead nitrate, and this would be sodium iodide, right? And the precipitate would be lead 2 iodide. And that's precipitate formed spontaneously, without anything additional happening. Okay, so what we're going to look at with regards to precipitation reactions is a couple of things. How do we predict a precipitate being formed? Now, in your packet in Canvas, in that packet of tables, you're going to have a page which contains this information right here. This is used basically to predict whether or not a precipitate will form. So if you look at this closely, you see that it gives you some information about different types of compounds. For example, the first line says, almost all nitrates, acetates, perchlorates, group 1A metal salts, and ammonium salts are soluble, right? So any compound which fits the criteria described in the first line would be soluble. Most chlorides, bromides, and iodides are soluble, but there are certain exceptions. Those of lead 2+, silver+, and mercury 1, all right? So, these are just basically rules that you can use to make predictions as to whether or not a precipitate will form when these ions are present in an aqueous solution. And this will become important for what we're going to learn about next, because what we're going to learn about next is how do we determine the net ionic equation for such reactions. And these are a couple of net ionic equations for precipitation reactions. For example, the aluminum ion coming together with the hydroxide ion to form aluminum hydroxide, the aluminum ion coming together with the phosphate ion to form aluminum phosphate, and so on and so forth. And these are just some reactions which have some industrial applications. For example, this one is used for water purification, all right? If you want to remove aluminum, then you simply add some base to it and you're going to get some gelatinous precipitation of aluminum hydroxide being formed, which you can scoop off or filter or whatever, all right? And there are other descriptions that are given here for the different reactions here. I won't go through all of them. I will leave that for you to read upon. Now, what I really want to get to right now is how do we determine the net ionic equation? So I'm going to start off with this example right here. All right, so here we have lead nitrate, lead 2 nitrate aqueous, and potassium iodide aqueous. And first thing we need to do is write down or figure out what the products are, and then we can go from here. Now, this reaction here will be a double displacement reaction. And if you remember from your introductory chemistry, whoops, okay, let me undo this here. Okay, so if you recall from your introductory chemistry, there will be a switching of partners. So the lead will come together with the iodide to form lead 2 iodide, and the potassium will come together with the nitrate to form potassium nitrate. So the next thing we need to determine is whether or not these compounds are soluble in water. And that means we have to go back to the rules that we learned before. So not this table here, as we said before, right? And one of the compounds formed is lead 2 iodide. And according to the second line here, most iodides are soluble, but one exception would be lead 2, right? So we can go back to this here and put in parentheses the state symbol being solid. All right. We do that because this is insoluble. All right. Now, as far as the lead, I'm sorry, as far as the potassium nitrate is concerned, if you go back to the table, you see that it says that almost all nitrates and group 1A metal salts are soluble, and potassium nitrate satisfies those two categories. So here, beside the potassium nitrate, we're going to put the state symbol aqueous. Oops. Aqueous. All right. So now we have all the state symbols in place. So the question now becomes, how do we get the net ionic equation? Now for these types of reactions, to get the net ionic equation, we have to pay attention to the state symbols that are present in each of these, for each of these substances, starting with the lead to nitrate. So key thing you need to remember here is that any ionic compound which is aqueous will dissociate to form their constituent ions. So in the case of the lead 2 nitrate, I'm going to write it here, it will dissociate to form lead 2 plus, aqueous, and please do not forget the state symbols, very important, plus 2NO3 minus, aqueous. And of course, we have the 2 here because of the 2 here, right? So this becomes 2NO3 aqueous. Plus, oh, I forgot one important step. We should balance the first equation here. So let me do that quickly. 2 here, 2 here. Very important. Okay, now that we have done that, for the potassium iodide, which is ionic and in an aqueous solution, you're going to have it dissociate to form 2K plus aqueous plus 2I minus aqueous. Okay, so that takes care of things on the reactant side. Let me erase this here. And then on the product side, you're going to have, you'll notice, PbI2 solid. So when you have a situation like that, this will not dissociate, so you simply rewrite it as it is, PbI2 solid, plus, and then we have potassium nitrate, which is in an aqueous solution, and therefore it will dissociate because it's ionic and in an aqueous solution to form 2K plus aqueous plus 2NO3 minus aqueous. All right. So the first equation is the molecular equation. The second equation is the ionic equation. So now we're going to get to the net ionic equation. And if you remember what we did when we looked at determining the net ionic equation for a acid-base reaction, we do the same thing. That is, we cancel out the common ion on both sides. And in this particular case, the common ions would be the nitrates here and here, the 2 nitrates here and there, and the 2 potassium ions here and here, right? So therefore, we simply write down what is left, which would be the net ionic equation. And that would be Pb2 plus aqueous plus 2I minus aqueous to give PbI2, hate when this happens, I2, erase this here. I2 solid. And this, ladies and gentlemen, will be the net ionic equation, all right? So that's basically how you determine the net ionic equation for a typical precipitation reaction. Okay, are there any questions? Any questions? Okay, if there are no questions, I'm going to move on. So the next thing I want us to talk about, which I think will be the last topic in this chapter, deals with redox reactions. Redox is the abbreviation for oxidation and reduction, all right? So first thing we're going to say here is that there are some reactions, not all, but some reaction which involves what we call changes in the oxidation states. And these oxidation states are represented by what we call oxidation numbers. Now, when it comes to monatomic ions, the oxidation numbers would be the same as the charge on the monatomic ion. So for example, in the case of Na+, the oxidation state for that sodium ion would be +1, all right? If it was chloride minus or Cl minus, then the oxidation state for that particular ion would be -1, all right? So basically, that's for monatomic ions. Very simple, all you have to do is look at the oxidation numbers. Now, when it comes to oxidation numbers for other elements, there are some rules that you have to follow, all right? And it depends on, of course, well, many things, including what the elements are combined with in a compound. So these are some of the rules for determining the oxidation numbers of different elements. The first one is that for atoms in a neutral species, the total of all the oxidation numbers will be equal to 0, all right? So it doesn't matter what the compound is, as long as it is neutral, then the sum of all the oxidation numbers of all the elements in that particular molecule or ionic compound is 0. The second rule has to do with elements in group 1A. Any element in group 1A which is combined with other elements will have an oxidation number of +1, all right? So that's basically a given. If you have an element from group 1A, meaning, and these are metals, not hydrogen. So we're talking about sodium, lithium, and so on, all those elements in that group, rubidium, etc., potassium. Those elements, when they're combined with other elements, their oxidation numbers are +1. Okay, the third rule is very specific. It has to do with fluorine. Whenever fluorine combines with any element or any other elements to form compounds, then the oxidation number of that fluorine is equal to -1, all right? Then we get to a rule concerning hydrogen. Okay, so in the case of hydrogen, when hydrogen is combined with any other elements, the oxidation number is equal to +1, with the exception of metallic hydrides. Now, in the case of metallic hydrides, the oxidation number of hydrogen in those compounds will be -1. So please make a note of that. It's not on the rules here, or not in the rules here, so make a note of that. When you have hydrogen combined with a metal, then the oxidation number of hydrogen in such compounds is -1. And then we get to the next rule, which says in most of its compounds, oxygen has an oxidation number of -2. Again, there's an exception. And the exception here has to do with peroxides, in which case the oxidation number of oxygen in those compounds will be -1, all right? So in all other compounds where oxygen is combined with other elements, the oxidation number is -2, but with the exception of peroxides, where in that case, the oxidation number of oxygen is -1. Okay, some other rules that you need to be aware of, and these have to do with binary, in other words, 2-element compounds, where one of the elements belong to either group 7A, 6A, or 5A. And as you can see, in such compounds, elements in group 7A will have an oxidation number of -1, elements in group 6A will have an oxidation number of -2, elements in 5A will have an oxidation number of -3, all right? So that's specific to these groups. And if you're talking about specifically elements from these groups that form binary compounds with metals, right? Okay, and then the last rule says most elements, other elements' oxidation numbers can be determined when they form compounds, including elements for which the rules are listed above, all right? So it's very important that you familiarize yourself with these rules. And I'm just going to work a couple of examples so that you can see how you can use these rules to determine the oxidation number of different elements. So let me clean this up. Okay, so the first example I'm going to use is Water, very simple example. H2O. And if you were asked to find out the oxidation number of each element present, well, it's very simple because the rules are very direct when it comes to hydrogen. The oxidation number of hydrogen would be +1, and the oxidation number of oxygen would be -2. So that's very simple, all right? That comes directly from the rules. And you'll notice that because water is neutral, the sum of the oxidation numbers will be equal to 0. In other words, 2 times +1 plus -2 gives you 0. All right? So that demonstrates another rule that we talked about, in that for a neutral molecule, the sum of the oxidation number is going to be equal to 0. Okay.
Oh, okay. And that's why hydroxide ions are have a negative charge. All right.
Exactly right. Exactly. In fact, we can look at that right now. OH minus, right? Now, in this case here, going according to the rules, hydrogen would be +1. I'm sorry, +1, and oxygen would be -2. But because the overall charge is -2, that's because +1 plus -2 gives you -1, which is the same as the overall charge for the hydroxide ions. So that's basically how that is done. Okay, let's move on to an example which is a bit more complex. So let's say you're given HNO3, and you're asked to find the oxidation number of each of these elements. Well, hydrogen, as we said before, would be +1. Oxygen will be -2, but there's no direct rule about nitrogen. So how do we find the oxidation number of nitrogen? Well, what we can do is call that X, all right? That's the oxidation number of nitrogen, that's X. And we exploit the fact that because this is neutral, the sum of the oxidation numbers here will be equal to 0. So this will be +1 plus X for the nitrogen, plus 3 times that for oxygen, which is 3 times -2, and that would be equal to 0. Why is this thing not writing? 0, okay. And all we have to do is a simple algebra solve for X. So that's 1 plus X minus 6 equals 0, which means that X minus 5 equals 0, which means that the oxidation number of nitrogen, which is X, is equal to +5, all right? So that's basically how you determine the oxidation state or number of nitrogen in this particular compound, all right? Any questions about this example? Any questions? Okay. Here's another example. Suppose you're given MnO4 minus. Minus, all right? So we know what the oxidation number of oxygen, it is -2, but for manganese, we don't know what that is, right? So we're gonna call that X again, all right? So this is X, all right? So based on the formula here, now we have to take into account, of course, that we have a negative sign, right? Which means that the sum of the oxidation numbers here for all of these will be equal to that negative -1. So X is the oxidation number of manganese plus 4 times -2, and the sum of that will be equal to -1. So X minus 8 is equal to -1, which means that X is equal to +7, +8 minus 1, sorry, which is equal to +7. So the oxidation number of manganese in this compound is +7. All right? Any questions about this one? Any questions? Okay, so I'm going to give you one to try on your own. Let's see if you can get this one. Suppose I gave you this. Cr2O7 2 minus. So how would you determine the oxidation numbers of each element present?
Do you want me to work it out on paper and then tell you, or just
Whatever. Work it out and then let me know.
I can probably do it in my head. So in this, I don't know the rules about chlorine. So
No, that's chromium. I'm sorry. This is
Chromium.
Yeah, CR. That's
okay.
my handwriting is not the best. Yeah, that's
It's
chromium.
fine. So the oxidation number of 7 in this is negative. The oxidation number of oxygen is that would be negative 14.
Okay, so
that
okay, all right. So let me do that here. So for oxygen, it's 7 times minus 2.
13. Oh, can you have fractional oxidation numbers?
You can, but that won't be the case here.
Oh, okay.
Uh-huh.
Let's see here. So we got negative 14 equals negative 1. Plus.
Remember, there are 2 chromium atoms.
Yeah. Yeah. 2x. So I'm getting 2x equals positive 13.
Oh, wait a minute. So you have 2x here plus 7 times minus 2 equals what?
Yep.
What goes here?
Negative 1.
Nope. Minus 2.
I messed that up. All right, then that's 12.
Okay.
All right, that
exactly.
Makes sense. So the oxidation number of chromium is 3.
No.
Well,
think about it.
Per atom. I mean, altogether it would equal 6, but wait.
No.
I guess it is. I guess it is 6.
Exactly, because 2x minus 14 is equal to minus 2. 2x would therefore be equal to 14 minus 2, which is 12, which means that x would be equal to plus 6.
Oh, so I don't know what I was doing there. Sorry.
Yeah, you have to be careful. You have to pay attention to the number of atoms. You have to pay attention to the charges, or the overall charge, and set the sum of the oxidation numbers equal to that charge, and then do your algebra from there. All right?
Oh, okay, cool.
So that's basically how you solve problems like this type. Okay. So that leads us to another topic. And that topic has to do with redox equations. All right? Or redox reactions, right? Now that we understand what happens or how we can determine the oxidation numbers, then we can determine whether or not an oxidation or reduction takes place. So let's first define what we mean by these terms, oxidation and reduction. So as stated here, oxidation occurs when the oxidation number increases for a particular atom, right? So if the oxidation number increases as you go from reactants to products, well, if you lose electrons or the oxidation number increases, that means that that particular atom is being oxidized. If the atom gains electrons or if the oxidation number decreases, then that atom is undergoing reduction, right? And the key thing you need to remember is that wherever you have oxidation, then somewhere in the universe you must have reduction, right? Because if something is being oxidized and it loses electrons, that means that somewhere in the universe, something is gaining electrons and therefore undergoing reduction. So you cannot have oxidation without reduction. One must occur simultaneously with the other, all right? Okay, yes, sir.
So for reduction oxidation reactions, is it just atoms exchanging electrons?
Exactly. Basically, it's a transfer of electrons from basically one atom to another. And as you're going to see, it's going to seem complex when you especially get the balanced equation, but fundamentally, it comes down to electron transfer from one atom to another. That's basically what happens.
But how do you?
I'm sorry?
But how do you tell when atoms will exchange electrons? Just It
Well,
seems.
you have to look at the equation, right?
Mhm.
And then when you look at the equation, you look at which atom has an increase in oxidation number and which atom has a decrease in oxidation number, right?
Oh, I see.
So the one that undergoes an increase in oxidation number, that atom is losing electrons. The other one that undergoes a decrease in the oxidation number, that atom gains electrons, right? And you're going to see that in this
Okay.
simple example here.
All right.
So in this example, if you take a piece of magnesium coil and you stick it in a solution containing copper 2 sulfate, right? And you sit for a while and wait, you're going to see a couple of things happen. You're going to see that the blue solution, which is the copper 2 sulfate, that solution clears up. So as you can see, it goes from blue to colorless or almost colorless, right? At the same time, you're going to see a deposit appearing on whatever is left of the copper in the solution, right? And that deposit will be the copper metal. I'm sorry, the magnesium is what is left. I'm sorry. The copper metal is what is being deposited, right? Now, let me give you the equation for this reaction right here. So basically, you have magnesium, which is a solid, plus copper 2 sulfate, aqueous, to form magnesium sulfate, aqueous, plus copper solid, all right? Now this is the molecular equation. I'm going to skip the ionic equation and get to the net ionic equation. The net ionic equation is Mg solid plus Cu2 plus aqueous to give Mg2 plus aqueous plus Cu solid. So this is a net ionic equation. This copper 2 plus ion is the blue, is responsible for the blue color, and magnesium 2 plus is colorless. All right. So basically that explains why the solution clears up, because the copper 2 plus will be reacting to form the colorless magnesium 2 plus, and you're going to see a deposit of copper solid on whatever magnesium that is left, right? So believe it or not, this is a redox reaction. And we know that because if you look at the magnesium here, going over here, you see that this magnesium here has no charge and the magnesium here has a +2 charge, which means that the magnesium is losing electrons, right? In fact, losing 2 electrons, right? So therefore, because it's losing 2 electrons, the magnesium is undergoing oxidation. All right? And then in the case of copper 2 plus, going from copper 2 plus to copper solid, it is gaining 2 electrons, which means that the copper 2 plus is undergoing reduction. All right? So this is a simple redox example of a redox reaction, right? The magnesium goes from 0 charge to +2, which means that it loses 2 electrons. So therefore, based on the definition of oxidation, magnesium is undergoing oxidation because it is losing electrons, and its oxidation number increases from 0 to +2. On the other hand, the copper 2 plus gains 2 electrons to form the copper solid, right? And therefore, the copper 2 plus is undergoing, according to the definition of reduction because it's gaining 2 electrons, because its oxidation number decreases from +2 to 0 on that side, all right?
Oh.
So that's basically, and you can see clearly, there's an electron transfer. The magnesium is giving up its electrons to the copper 2 plus, and therefore that's how you have the redox taking place, all right?
Yeah, this makes significantly more sense than the last time I read about it.
Oh yeah, it's very, like I said, it just comes down to the transfer of electrons from one substance to another, all right?
Okay.
That's basically what redox is all about. Okay, so that's a simple example, but of course, as you can imagine, things can become a bit more complicated. Let me go to the PowerPoint here and see what's up next. Okay, so we're going to get into balancing redox equations. Now, I must admit, this information here is not the greatest. So it doesn't clearly indicate how to balance the equations of this type. So in my opinion, the best way to go about learning this process is to jump directly into an example. So let me go back to my writing pad. So let me just give you a typical redox problem you could be given, balancing a redox equation. Let's say you're given CR2O7 2 minus plus Fe2 plus to form CR3 plus Fe3 plus. All right, so this is a typical unbalanced redox equation, and you could be asked to balance it. All right, so these are the steps that you have to go through in order to balance a redox equation. The first step is that you separate this equation into two half equations, right? One half equation would be oxidation and the other half equation would be reduction. So in this particular case, the way we separate it is that we write down the CR2O72 minus to form CR3 plus and the Fe2 plus to form Fe3 plus. Fe3 plus, all right? So that's the first step in this process. You separate this equation into two half equations, all right? The next step is that you balance all atoms excepting oxygen and hydrogen in the traditional way that we're accustomed to. So what that means in the case of the first half equation is that since you have two chromiums here and only one here, you simply put a 2 here, all right? In the case of the second half equation, there's no need to do anything because the ions are already balanced. You have one on both sides, all right? So that basically takes care of balancing those atoms other than oxygen or hydrogen. Now we get to balancing the oxygens. How do we balance the oxygens? Well, we basically add water to the side that is deficient of oxygens, and we add enough water molecules so that the oxygens are balanced. So what does that mean for this half equation here? Well, we have 7 oxygens here, so that means we need to add 7 water molecules on this side to balance the oxygens. Because by adding 7 water molecules on that side, we're adding 7 oxygens on this side, which balances with the 7 oxygens on that side, all right? Now for the second half equation, we don't need to add any oxygens, we don't need to add any water because there are no oxygens. So we leave that alone, all right? So that leads us now to balancing the hydrogens. How do we balance the hydrogens? Well, we basically add hydrogen ions to the side, which is deficient of hydrogens until the hydrogens are balanced. So for the first half equation, we have a total of 7 times 2, 14 hydrogens. So that means over here, we add 14 hydrogen ions. Oops. All right, we add 14 hydrogen ions on the right side to balance with the 14 hydrogens on the left side. Again, in the case of the second half equation, there are no hydrogen atoms, so therefore there's no need for us to balance the hydrogens since there are none. Okay, now the next step is where students tend to make their mistakes, especially when they're under test pressure conditions, all right? So please try to follow what I'm going to say about the next step. The next step has to do with balancing the charges, all right? How do we balance the charges? We balance the charges by adding electrons to the side which has a higher net charge, all right? And we add enough electrons so that the charges are balanced. Okay, so what does that mean for the first half equation? If you look closely at the first half equation, you notice that you have 14 plus charges here, and we have a -2 here. So the total number of charges on the left side would be 14 minus 2, which would be plus 12. So we have a total of plus 12 charges on the left side. On the right side, we have 2 times plus 3, 6. There are no charges provided by the water, so therefore the total charges on the right side will be plus 6. All right? So how do we balance the charges? Well, since we have a higher net charge on this side, then that means that we need to add electrons to this side. Now, each time you add an electron, you're adding a negative charge. So therefore, when you add electrons here, you're reducing the charge here by, the total charge here by 1. So therefore, in this particular case, since you want to have the charges on both sides be equal, right? That means that we would add 6 electrons to this side, because by adding 6 electrons, we're adding 6 negative charges, which reduces the total charge to plus 6, which balances with the plus 6 on the other side. All right? Everybody understands that? Any questions about that?
When we did the chromium and oxygen before, we separated the chromium and the oxygen and figured that the oxidation number of 7 in total was negative 14.
Okay.
Why isn't that the case in this?
Well, it is still the case, but what we were concerned with is the overall charge on either side of the equation. So this is the left side here.
So
this is the left side.
So
we're not concerned with the charges within the formula. We're concerned with the total charges within the compound or on the side of the equation. So in this case, we added up all the charges to get plus 12 on the left side, and then on the right side is plus 6. So we need to reduce the plus 12 to plus 6 by adding 6 electrons. All right, and therefore now we have the charges balanced on both sides. All right. Now, in the case of the second half equation, it's actually very simple because we only have a plus 2 charge here, we have a plus 3 charge here, which means that we simply add a negative charge here or an electron to reduce the total charge here from plus 3 to plus 2, which balances with the plus 2 on this side. All right. So that's basically how we balance the charges. Okay. Now we're not finished yet. Let me just erase some stuff here, because the next step is that we have to ensure that the total number of electrons lost and gained are the same. If you remember when we talked about the magnesium and the copper reaction, the number of electrons lost and gained is plus 2. But you'll notice, you'll notice that in this case here, we have 6 electrons here, and we have only 1 here, right? So how do we make sure that the charges are the same? Well, we simply multiply this equation here, 6 Fe2 plus. To give 6 Fe3 plus 6 electrons. All right. So now we have 6 electrons here, which will cancel out with these 6 electrons here. Let me just cross this up just to avoid confusion. So basically all we have to do from here is add both equations together without whatever is common to both sides, which would be the electrons in this case. And we simply write down what is left. So we're going to be left with 14H plus Cr2O7 2 minus plus 6 Fe2 plus to give 2 Cr3 plus plus 7H2O plus 6 Fe3 plus. And that should, and that, folks, should be the final answer. All right? However, I always tell my students, no matter how confident you are in your final answer, check to make sure that your final answer is correct by making sure that everything is balanced, right? All the atoms are balanced and all the charges are balanced. So let's do that now. If you look on this side, you have 14 hydrogens, right? On this side, we have 7 times 2, 14 hydrogens. So we know the hydrogens are balanced. Here we have 2 chromiums. Here we have 2 chromiums. All right, so the chromiums are balanced. Here we have 6 oxygens. And here we have 7 times 1, 6 oxygens. So the oxygens are balanced. Here we have 6 irons. Here we have 6 irons. So the ions are balanced. And then we have to balance the charges, right? We have to make sure the charges are balanced on both sides. So here we have 14 plus charges, so that's plus 14. Here we have a minus 2, and here we have plus 12. So what does that give? 14 minus 2, that gives you 12 plus
24.
That gives you a total of plus 24. And then on this, we have plus 6, and we have 6 times plus 3, so that's plus 18. So that gives you 24, plus 24 as well. So now we know the charges are balanced and everything is balanced. So we know that the equation we got is correct. All right. Any questions?
In this.
Any questions?
Yeah. Yes. Where did the hydrogen come from?
Okay, so I think you're talking about, why is this thing? You're talking about balancing these hydrogens here, right?
Yeah, on both sides. I mean,
right.
The original equation doesn't have hydrogen in it, so.
Okay, that's what I'm saying, right. Okay, the hydrogens were introduced because we had to balance the oxygens. Remember we said that we had 7 oxygens. Where is my pointer? Okay, something, I can't find my pointer. Where is it? Oh, okay, I found it. Okay, remember we said that there are 7 oxygens here, right?
Mm-hmm.
So to balance the oxygens, we introduce 7 water molecules. I hate when this happens.
Okay.
Right. Okay. Anyway, right. So that's where hydrogens were introduced. The hydrogens right side to balance with the 7 oxygens on the left side. All right. And then we have to balance the hydrogens. So since we have 14 hydrogens here, 7 times 2, 14, that means that we have to balance the hydrogens. Okay, I see that thing. Let me get rid of it. We have to balance the hydrogens by adding 14 hydrogen ions here. Mm-hmm. All right. So that's kind of important as well. To balance the oxygens, we add water to the side that needs the ions to balance it. And to balance the hydrogens, we add hydrogen ions to the side that needs hydrogen ions to balance the hydrogens.
I see.
All right, so that's basically what it comes down to.
If you were doing this with compounds that didn't have oxygen or hydrogen in them, would you use another neutral compound?
No, if like as we said, in the case of the second half equation, there were no oxygens here, so we don't need to add any oxygens or add any water, so we just leave it alone. And the same is true. There are no hydrogens on one side.
But
or the other, then you don't need to add any hydrogen ions. So,
well, say you had, instead of 7 oxygens, you had, let me think here, 14 fluorines, or what some other.
Well, right. Okay. Well, the fluorines would have to be existing on both sides, okay, right? If it was any other atom, apart from oxygen or hydrogen, those atoms would have to be existing. So, that's why, if you remember when I was talking about the rules, I said the first step is that to separate separate the equation into 2 equations. The step is you balance all other atoms excepting hydrogen and oxygen, right? And those atoms would have to be in existence in the equation in order for you to do that. And then you worry about balancing the oxygens, and then you worry about balancing hydrogen, right?
Okay.
Let me do another example so that no problem. So let's say you're given, MnO4 minus plus N2 to give Mn2 plus, you know what, I need to learn how to disable this function. Mn2 plus NO3 minus. Okay, so let's say you're given that and you're asked to balance this equation. So you remember what the first step is? First step is what? Anybody? What's the first step?
Separate the two equations.
Okay, so you separate into two half equations. So one half equation would be MnO4 minus to form Mn2 plus, and the other half equation is N2 to form NO3 minus. Okay, very good. So what's the next step?
Well, it looks like there's oxygens in both of those equations.
Stick a pin. But before you balance the oxygens, what's the next step? There's a step before balancing the oxygens.
Trying to balance. Oh, just balancing the equation in general. We would need to.
Right. You balance all atoms excepting oxygen and hydrogen, right? So in the case of the first half equation, you have one manganese here, so you don't need to do anything here. But in the case of the second half equation, you have two nitrogens here and one nitrogen there. So what would you do in this case?
You would say 2 nitrogen, oxygen 3.
Right, very good, right. So that's basically, you need to remember that. You need to balance all atoms other than nitrogen other than oxygen or hydrogen in this step, right? Okay, so the next step would be what now?
Then we would balance the oxygens.
Okay, so what does that mean for the first half equation?
Well, in the first half equation, we would need to add 4 oxygens.
Okay, and how would you do that? And to which side would you add?
You would add them. Oh, you would add. Let's see here. 4 water molecules to the right side.
Exactly, 4 H2O on the right side. Okay, what about the second half equation? And think carefully about this one. How would you balance the oxygens in the case of the second half equation?
You would have to add 6 water molecules to the left side.
6 H2Os on the left side. Very good. Okay, next step is?
Then we need to balance the hydrogens.
Okay, so how would you balance the hydrogens in the first half equation?
Okay.
To which side would you add hydrogen ions and how many?
So we would need to add 8 hydrogen atoms to the left side.
Exactly, 8 H plus ions on the left side, all right? And what about the other half equation?
We would need to add 12 hydrogen ions to the right side.
Exactly. All right, very good. What's the next step? Now, as I said before, the next step is where students always screw up. I don't know why, but students have a difficulty with balancing the charges.
Then we need to add the right number of electrons to, well, we need to calculate what the charge of each side is and then figure out where we need to add electrons.
Okay, very good. Okay, so what's the total charge on the left side?
That would be +7, I think.
Exactly, +7. That's 8 minus 1, right? What would be the total charge on the right side?
That's 2, +2.
+2, okay. So to which side would you add electrons and how many electrons would you add?
You would add 5 electrons to the left side.
Exactly, 5, so +5 electrons here. And the reason why is because by adding 5 electrons, you're adding 5 negative charges, which reduce the total charge on that side to +2. which balances with the +2 on this side. Okay, very good. What about the second half equation? What's the total charge on either side, starting with the left side?
On the left side, it's 0. So we would
Okay.
need to
What's the total charge on the right side?
10.
Exactly.
So we need
12
to add
minus
10
2, so
electrons.
to which side?
The right side.
Exactly. So you're going to add 10 electrons to the right side. Okay. So that balances the charges. Very good. Okay. So what's the next step? You remember what we did in the next step?
Well, then we need to add the equations together. No?
There's something we need, a very important step that we need to take before we add them together. Anybody? Very important step. If you don't do this step, everything else will be incorrect.
Would it be to cancel out any similar?
No, before you even do that, let me do this. Let me give you a little hint. Hold on, let me do that first. Let me give you a hint. You see this here?
Mm-hmm.
And do you see this here?
Yeah.
Okay, what do you notice about those two?
Oh, do we need to cancel electrons?
Yeah, but before we cancel, we need to do something. Before we do any cancellation of anything, there's one important step, very important, and it has to do with the electrons.
Dang, I must confess I'm stumped.
Anybody else? Anybody else? Remember what I said earlier? I said the number of electrons lost and gained must be what?
Equal. Okay.
Exactly. And they're not equal because you have 5 here and you have 10 here. So what you have to do is try to make sure that the number of electrons are equal that are lost and gained. And in this case, what this means is that you multiply this by 2. So you have to multiply the entire equation by 2. So when you do that, you're going to get 10 electrons plus 2 times 8, 16 hydrogen ions plus 2 MnO4 minus. And then on the right side, you're going to have 2 Mn2 plus 8 H2O. Right? And then you can do your cancellation, right? So the 10 electrons here and here will go. There's some other items that will cancel. For example, these 6 water molecules will cancel out 6 of these, leaving behind 2, right? And these 12 hydrogen ions, oh, I thought rain was falling. These 12 hydrogen ions will cancel out 12 of these, leaving behind 4, right? And then we add them up. We add what's left, and that would be N2 plus 4 hydrogen ions plus 2 MnO4 minus. Okay, and then on the right side, you're going to have 2 NO3 minus. NO3 minus plus 2 Mn2 plus 2 H2O. And that should be the final answer. But again, as I said before, we need to check that everything is balanced, including the charges. So let's do that now. We have 2 nitrogens here. We have 2 nitrogens here, so that's balanced. We have 4 hydrogens here. We have 2 times 2, 4 hydrogens, so that's okay. We have 2 manganese here, 2 manganese here, so that's okay. And then for the oxygens, we have 2 times 4, 8 oxygens. We have 2 times 3, 6, plus 2, 8, right? So the oxygens are balanced. And then as far as the charges are concerned, we have plus 4 minus 2 gives you plus 2 on this side. And here we have minus 2 plus 4 equals to +2 on this side. So everything is balanced.
Hmm.
So that's
Okay.
basically how that is done.
I think I
All
got
right.
it now.
Yeah. So you have to follow each step religiously. If you screw up on one step, that basically, destroys your answer, your subsequent answer. Okay. Any questions about this example? Any questions?
Mm-mm.
Okay. I'm going to put one on the screen for you guys to try. Okay. So suppose you're given, hold on, let me see. Oh, what's a crackling sound?
Oh, that was my my microphone. Sorry, I'll turn it off.
Okay. Okay, let me see. I'm trying to make up one here. This is something I'm making up. Okay, suppose you're given uh, NO3 minus plus S2O3 2 minus to form NO2 minus plus S4O6 2 minus. Okay, I think that will work. Yeah. All right, I'm going to step away for a while. I want you guys to try this. And then when I come back, I'll ask you to tell me how you would have solved this. All right. So I'll be back in the next couple of minutes. All right. Oh, okay, let's see here. Okay, folks, I'm back. So, has anybody solved this problem? Well, what's the first step? Well,
Not quite.
I showed you two examples, so you should at the very least know how to start this process.
I've started. I'm just still working on it.
Okay. At least give me the start. What's the first step?
Oh, sorry, my
Mhm.
mute was on. I need to separate the equations and then balance them
Hold on.
molecularly.
Let's separate them first. So NO3 minus to NO2 minus, all right? And then S2O3 2 minus to S4O6 2 minus.
Yeah, I got
All right.
that.
Mm-hmm.
So
Okay, so what's the next step?
I would balance them molecularly. So, on
You
the
balance all atoms excepting oxygen or hydrogen.
so
Okay.
the top equation's already balanced.
Okay.
The bottom equation, I would multiply the left molecule by 2.
Okay. Okay. So far, so good. What's the next
Okay.
step?
Well, then I need to balance my charges.
Nope.
No?
You're a couple of steps ahead.
Fudge.
What do you need to
Well,
balance?
oh, I need to balance the oxygen.
Right. Okay. So how would you balance the oxygen for the first half equation?
Oh, I would add I would add a hydrogen atom.
Nope.
Or not a hydrogen atom, a water atom.
Right. Water molecule. And you would add it to which side?
To the right side.
To the right side.
That's where I was tripping.
Yeah. And what about the second half equation? How would you balance out? How would you balance the oxygens?
Oh, it's the oxygens are already balanced there.
Very good. Okay, so there's no need for you to add water to that side. Okay, so what's the next step?
All right, so the top equation, the charges are no longer balanced, so
you're skipping a step. You're skipping a step, man. You're skipping a step.
Damn it.
Before you balance the charges, what do you balance?
Oh, sorry, I forgot to say that. I would add 2 hydrogen atoms to the left side.
Right, and it's not hydrogen atoms; it's hydrogen ions.
Hydrogen ions. I'm sorry.
Right.
All right. So.
And what about the second half equation?
It still doesn't need any.
Exactly, no hydrogens. Right. Okay, so what's the next step?
I think I finally got to balancing the charges this time.
Okay, very good. So how would we go about balancing the charges for the first half equation?
All right, so the two hydrogen ions plus the NO3 ion makes plus 1.
Plus 1 on this side.
And the water molecule has no charge, so the NO2 has a -1 charge. Okay,
good. So how would you balance the charges? In other words, how many electrons and to which side would you add electrons?
So it looks like I'm going to have to add 2 electrons to the left side.
Exactly. So add 2 electrons to the left. Whoops, 2 electrons. Okay. Right. What about the second half equation?
All right. There, I see. I guess I skipped a step in the middle. So on the left side,
Mhm,
there is a -4 charge, and on the
mhm,
right side, there's a -2 charge.
mhm.
So I'm going to have to add 2 electrons to the right side.
Exactly. 2 electrons to the right
Ah,
side.
all
Okay,
right.
what's the next step?
Now it looks like all right, my electrons are balanced on both equations, so now I
Exactly.
would add them together. I don't have
Exactly.
to do any
Right.
multiplying.
Yeah, we looked out on this one. I mean,
Mhm.
I totally just created this one out of my mind. I didn't know what the answer is going to be, so I didn't anticipate that this would be so easy. Right. And I don't think there's anything else to cancel out, right? So we just write down what is left. So that would be 2H plus
NO3
plus NO3 minus plus
plus
2S2O3 2 minus to give NO2 minus plus H2O plus S4O6 2 minus. And then of course we have to check to make sure everything is balanced. 2 hydrogens here, 2 hydrogens there.
2 plus
Nitrogen is here, nitrogen is
-1.
here. We have 3 plus 6 oxygen, so that gives you a total of 9 oxygens.
-1.
We have 2 plus 1 plus 6, so that's 9 oxygens. We have 4 sulfurs, and then the charges, we have +2, -1, -4, so that gives you what?
Oh,
that gives you -3,
and it balances neatly.
and -1, -2, -3. So yeah, everything is balanced, all right?
Cool.
So that's basically how you go about balancing equations, all right? Okay, that's pretty much all for today. Now, before you guys leave, well, firstly, let me take roll to make sure I capture everybody's attendance. So let's see who I missed or who came late or whatever. Is Rios here? I don't see her. Canon.
Yep, she is here.
I'm here.
Oh, okay. Chang, Chavis, DeGraff, Franklin, Han, Panic, Rees, Gross.
I'm here.
And Gross is here? Oh, yeah.
Yeah.
Sorry, okay. And Smith. Okay, so before you guys leave, let me say that a couple of things. So if I'm not mistaken, your first test was scheduled for next week, right? So what I plan to do is, because there's one more quiz I want to give you before that test, because, well, let me just say this. The test is going to be based on chapters 1 through 3. And there's one topic that I have not given you a quiz on, and that's the topic of stoichiometry, percent yield, theoretical yield, and stuff like that, right? So I need to give you one more quiz based on that, and then the test will be based on chapters 1 through 3, as I said before. I think I told you guys that the tests will be take-home variety. So what I'm going to do is post it on Monday, and you have the option of completing it by the end of that week, which will be the Friday. All right. So that's basically the plan. And another thing I want to say too is that I had originally planned to scan and send back to you guys the graded work, because some of you were, I don't remember if it was this class or another class, some students were asking about feedback and so on. I have some scanner issues at the moment, but I hope to have them rectified by, if not today, definitely by tomorrow. So I'm going to send you back your individual completed work with the grades, and then you can see where, you know, you may have made some errors. And if, of course, if you have any questions, you know, concerning your graded work, you can, of course, contact me and ask me about that. I think that's it as far as announcements are. Oh, and another thing too, which I know I talked to you guys about it already, but if you're interested in joining the STEM club, please just send me an email expressing your interest. A couple of you from this class have done so already, so I appreciate that. You should expect something soon in terms of being added to the STEM course and so on. So look forward to that. You have a
I did
question?
have, yes, about, what was it? Quizzes 3 and 4.
Mhm.
And just to make sure, quiz 3 is like a fill out table of,
Hold on, let me refresh my memory about that.
I don't know if you can see that.
I'm going to go to the course itself and see what I posted. Okay, quiz 3. Oh yes, okay, so the first page, and I forgot to create a space for you guys to write your names and so on. Oh shoot, I actually posted the solutions. Oh, you guys got a break. Okay, anyway, you can complete that and turn it in. Let me
Okay.
see, quiz 4. Quiz 4. Okay, so quiz 4 has to do with relative atomic mass. So yeah, so yeah, that's basically what those quizzes
Yeah.
are, yeah.
Yep, there's just 2 questions on quiz 4.
Yeah. Mm-hmm.
Oh, okay, cool.
Yeah.
Well, I've completed both of them, and I shall be turning in quiz number 3
Mhm.
in just a few minutes.
Okay,
Cool.
no problem, no problem. Okay, any other questions from anybody else? Any other questions? Okay, so if there are no other questions, that's basically it for today. So I'll see you on Thursday. All right, so take care. Enjoy the rest of your day.
You too. Take care.
Mhm.